sixth session of the webinar series from Reliable Process Solutions. And today we're going to start out talking about preventive maintenance. One of the key things that we need to do in all of our processes have a good preventive maintenance program. But sometimes we need to understand what preventive maintenance we need to do and actually why we're doing that preventive maintenance, because it's key to understand why we do these tasks. We just can't do the task because it's something that everybody does. We can't do the task because it's something our OEM people tell us we have to do. We have to have more justifications and reason for that. So today we're going to talk about preventive maintenance. But again, I always put this slide in there, all the things we do in the company, with RCM facilitation, with predictive and proactive maintenance. We've done lubrication this year, which is very important. I think next month we're going to talk about, or sometime in the next couple of months, about asset criticality and the importance of that. But that's going to also help us determine what preventive maintenance we do. But we have to get some foundation or some process to develop our PM programs, or at least think about that before we move into the next couple steps that we'll talk about over the next few months. So again, we look at our PF curve. The more maintenance we're doing on this right side of the curve in the reactive area, finding out things that are failing by human senses, the less effective and efficient we'll be. We've talked about predictive maintenance and the importance of using the new tools like mechanical ultrasound, vibration analysis. We've talked about oil analysis. So now we're over here and we're talking about things in our proactive area. We've covered lubrication excellence. We've covered all these areas in the proactive area. And we're just keep moving down the line here. We're not going to get to all of them this year, but hopefully everybody can get on the webinars next year. We'll cover more of these in detail. But again, moving down this curve, and we see our PM task across this curve. And we need to remember, our PM tasks are going to change as we become more reliable and become more effective in maintenance. We can't just keep doing the PM tasks we've been doing for the last 20 years and expect to have good results. So again, we're going to move down our slides here. But why are we doing all these things? Why are you guys on this webinar? Why are companies looking at reliability? Well, we have to be competitive. We talked about this slide early in the presentations that we started in the webinars. We have to be able to compete. But we're competing with this vehicle or a plant that's on the left-hand side of this curve. We're 30, 40, 50 years old in a lot of our facilities. We're not the Lamborghini type plant. And sometimes we can't afford to change our plant to the Lamborghini style. So we have to do effective maintenance. We have to do the right maintenance on the right equipment at the right time. We have to make this plant on the left-hand side here very reliable. We have to operate it very effectively in order to be able to compete in today's market, because we are competing around the world. So preventive maintenance. This is maintenance performed on a time-based or condition-based strategy. How do we know what tasks to do? Well, let's look at the reasons we do preventive maintenance. Why are we doing these tasks we call PMs? Well, like it says here, everyone has a PM program. All the plants I've been in around the world, they all have a PM program. One of the very first questions I ask when I go in, besides trying to find out how much reactive work they're doing, is, do you have a PM program here? Everybody has one. And then I try to find out, how was the PM program developed from day one? We have different kinds of PMs or different reasons we do PMs here. We do PMs based on time. So we have all these time-based PMs. We have a lot of condition-based PMs where there's something happening that requires us to do this task. We're going to look at failure finding tasks. What are those? What kind of PMs are failure finding? And then this is the one that most often is the big downfall. We do PMs because the OEM, the original equipment manufacturer, directs us to do these tasks. Are they good? Some of them are, some of them aren't. And then we're going to talk about hand-me-downs. These are things we've been doing for the last 20 years, based on experience or failures. Are they the correct PMs? A lot of times we have regulatory PMs that are required by our environmental groups, by OSHA, by safety standards. Those are some we have to do, but sometimes we have to use some common sense around those also. And then a lot of the PMs we do are just based on risk. We have this high dollar piece of equipment. Maybe it's a $250,000 centrifuge. Maybe it's $1 million gas turbine. And we're doing PMs just because the machinery is high risk, high failure cost. So what are those reasons? Well, the time-based PMs we talked about, they're PMs performed on some time frequency. We may do them every day. We may do them every week, every month. We may have quarterly PMs we do. Some PMs we do yearly. That's the only time we can open the equipment up, or on our scheduled annual outages. So there's all kinds of time frequencies we use on PMs. But the question is, how was the PM frequency determined to begin with? Why do we do it every week or every month? So there has to be some process in place to determine, why did we select that frequency? Now we have these condition-based PMs. These are tasks performed based on a condition. Noise, we may make an adjustment. Looseness, if something's loose and moving around, there may be an adjustment we make. A lot of times we do PMs based on measurements. We actually take a physical measurement with some kind of a tool, and we do the PM based on that measurement. There's a lot of times we can only do PMs when the machine's not operating. So another condition, sometimes we want to do the PM when the machine's at full load. It's like when you're taking, we talked about that in the predictive class, when you're taking predictive readings, it's better to take the predictive reading when the machine's at a full load. Now, I've been in a number of companies where they only do the PMs and the PDMs on a monthly shutdown when the equipment has no load on it. Well, it's not a good time. It may be the only time they can do it. It's not a good time to do it. Machines, when they're running under full load, is when we should do the PM or PDM task. This is going to give us the best information. What about failure finding task? It says here, a failure finding task is a task put in place to find a component that has failed, but maintenance or operations are not aware of the failure during normal operation. So some examples of these: a high level switch in a tank. When the liquid gets up to the high level switch, it does some action. It shuts a pump off or closes a valve. How do we know that that switch is going to work when we need it to work? Well, the best way is we have to test it. A high temperature switch. How do we know the high temperature switch is going to activate when it needs to? High pressure switches. When the pressure gets up to a certain point, how do we know that switch will actually function? The pressure relief valves on your boiler. They're all set at, maybe they're set at 220 PSI. How do we know they'll actually relieve? Emergency stop switches are another example. A lot of plants I go into, I've seen up to 6 or 8 emergency stop switches on one operation, depending on where the operator's at. How do you know that switch will work? If the operator gets a shirt sleeve, drops a tool, how do we know that switch is going to work? Well, the only way we know these are going to work is to actually test them. So in your plants, if you have equipment components like this, those are called failure finding tasks, and they should be labeled that way. They're PMs, yes, but you're looking for a component that can fail that you don't know has failed. If you look at these 3 major incidents around the world, you have Chernobyl on the left-hand picture. Here they were supposed to be performing some PM task on this nuclear reactor. They were actually supposed to be testing that the rods on the nuclear reactor would open and close when they needed to. And again, what happened here is they ran this plant around 3 years without doing that PM task. So one day they decided we better do our PMs on the rods. Well, they took, the way you do this PM is you close the rods all the way and confirm that they close. You open the rods all the way, confirm that they go to wide open, and then you go back into control. Well, on this particular day, they closed the rods all the way. When they drove the rods to 100% open, the rods stuck at 100% open. The reaction started carrying away. Well, that day, they hadn't scheduled very well because maintenance had one of the main cooling water pumps tore down for maintenance. They didn't have enough water to cool the reaction, and they had the nuclear meltdown. Nearly somewhere around 125,000 people were killed in that incident, and another 400,000 injured where they died later or had complications the rest of their life from the nuclear exposure. BP Texas City in the upper right-hand corner. Again, on the reactor you see in the center of the screen there. They started filling the reactor. That square box you see in front of the reactor was a heater. Well, the level transmitter went to 40%. It stuck there. The operator seen it not filling. He opened the valves up some more, ended up putting more heat on the heater. The reactor eventually overflowed to the flash pot you see on the right-hand side, the little skinny stack. Level transmitter in the skinny stack didn't work to light the flare. And there was a high-level switch in the reactor itself that didn't react. So 3 electronic devices failed that day. And due to that reaction, there was 15 people killed, 12 contractors and 3 operators. So again, failure finding task. Many of you on the call, I don't know how old you are, but the lower right-hand corner is Bhopal, India. Again, a reactor where a temperature switch has the first redundancy failed, a pressure switch has the second redundancy failed, a pressure relief valve, the third redundancy failed. And when this tower blew up, it killed around 20,000 people, including operators and all the people in the village next door to the plant. Highly toxic chemical. So again, 3 redundant systems that weren't being checked, PMs weren't being done on them, and lots of people lost their lives that day. So again, these are called failure finding tasks. You don't want these things to happen in your plant. You don't want an emergency stop switch that's there for a reason to fail. So again, very important PM task. So look around your plant, how many of these do you have? Now we have these OEM directed PMs. These are PMs performed based on information supplied from your original equipment manufacturer. And a lot of you know when you look in the back of that book, there's a whole list of PMs you're supposed to do. But how many of those PMs actually find failures? How many of those PMs actually extend the equipment life? You know, are these PMs just developed to minimize warranty claims by the OEM? And what I mean by that is a lot of times a component will fail in its warranty stage. You call the OEM up and he'll start asking you questions. What did you do this PM? Did you do this task? Did you do this task? Well, if you haven't done some of those, you're not going to be able to get the warranty claim. So again, but most of them add no value. I remember the company I worked for, I worked there for 25 years. And during that 25 years, I never collected on one warranty. One of the reasons I'd make the call, I didn't really have time to go through all the steps, and I hadn't done all those PMs maybe, so I wasn't able to collect. Well, the company I work for now has a law firm. There's 4 lawyers on staff that collect warranties, and there's a payback of that in a company as large as they were because they have a lot of warranty claims. So most of the time when a lawyer calls you trying to collect a warranty, there's a 50% chance you're going to collect that warranty. But again, it says here on the bottom, 30 to 40% of all OEM PMs add no value or find no failures. What about hand-me-downs? These are PMs that have been developed over the last 10 or 40 years, depending on how old your plant are, based on some failure or something that's happened in the past. These are some of the comments I hear. Well, we've always, and I got a misspelling here, I said, we've always done these PMs, so let's keep doing them. Or you hear comments, we've been doing these PMs for 20 years, we can't stop now. But we have to look at the PM. Many of these PMs add no value. They don't really find any failures. They don't keep the equipment from failing. So that's what we have to look at. Now, a lot of times at our plants, we develop PMs. We have a failure, and we say, well, we better develop this PM so that doesn't happen again. A lot of times you don't do the root cause analysis. Maybe you don't really know what that PM should have been. Maybe you're not even doing the right PM. Or maybe that failure was outside of the normal, something normal, and we're doing a PM for no reason. So again, hand-me-downs are sometimes PMs that we really don't need, add no value. Now, like I said, a lot of your regulatory PMs required by the EPA, OSHA, MSHA, fire insurance. A lot of times we have to do PMs, based on what these organizations recommend. But in some cases, maybe they aren't the right frequency, maybe they aren't the right thing to do. Now, I'll give you an example at the facility I came from. We had 2 coal-fired boilers there. Of course, the boilers have pressure relief valves on top. The inspector came in every year and he asked me the same question every year. Have you pulled the lever on your pressure relief valves to make sure they work? And I go, no. And he says, that's required by law, you have to do that. My comment was always, I'm not going to do that because every time I pull the lever to test the relief valve, it leaks by. And it leaks until I can get down on the next annual shutdown to change the valve out. So I said, I'm not testing them manually. And he says, well, it's required by law that you do that. I said, what's my other option? Well, if you don't do that, you have to change them out every year or every 2 years and rebuild them. So I took that option. Every year when we did the annual shutdown, I just replaced one or both of the pressure relief valves, sent them in for a rebuild inspection, replaced them with new. But that was better than the valve leaking by and the leak getting worse as the year and a half went on. So again, sometimes what's stated by law, maybe there's another option. What about risk? These are tasks we perform because the equipment is very expensive, has a high risk for some reason. Maybe those are potential for explosion. Maybe there's a potential for fire. Maybe there's a potential for release or it can cause a death. Some of these, you may want to increase the frequency, but still we have to look at these. Why are we doing the PM? Are we just doing it because of risk? What are we actually looking for? A lot of times I've found plants where they're doing these and they do them yearly. Well, on high risk situations where you can have an explosion, a fire, or a death, is yearly too far? Is it too long? So sometimes risk. I was just recently at a plant in Canada where they had a big electrical fire in one of their switchgear boxes. Fire caused a lot of damage, destroyed the whole switchgear. Luckily, they had some stuff that was still in stock from when they built the plant. Otherwise, they'd have been down for weeks. They were only down a couple of days rebuilding this. But I asked the question, when was the thermography scheduled? Well, it was scheduled for a week or two from when they had the incident. And I said, how often are you doing the thermography? Once a year. Well, is that the right frequency for the risk? Maybe not. In the company I came from, we started off years ago doing them every year. We went to every 6 months. We did thermography and electrical quarterly because there's fines. There's things that can happen a long time over a year. So is the frequency of thermography yearly good for this facility? Well, no, it wasn't. So we've changed the frequency because they can't afford to have an incident like this again. But here's activities of PMs. I put some of these in here so you can train your maintenance people with some of these slides. But activities of preventive maintenance, routine functions performed at regular intervals of time or life cycles. Lubricating is a good PM task. What about cleaning? A lot of times maintenance people say, well, it's not my job to clean, but sometimes you can't find failures without cleaning. So the operator or the maintenance person is going to have to do some cleaning to find the failures. They can be inspections, either visual by measurement or preventive maintenance tasks. Adjusting to some specification. A lot of the equipment in the industry, you have to make an adjustment once in a while to keep it within the spec. That's a PM task. Replacement of parts due to ordinary wear. V-belts might be an example of that. V-belts wear at some rate, and when they get to some point, we have to do that PM and change them out. All PMs, we should be looking for some early identification of a potential problem. And then the last one, a key. How do you document the PMs you perform? Is it just a checkbox that says I did it? Or are you putting some information along with that to say that you've done the task correctly and what you found? So those are activities. Now, John Mitchell wrote this book, Physical Asset Management Handbook. It says a PM can be cost effective when equipment operation is consistent, which means you can't operate the equipment two days or 5 days a month and develop an effective PM. Your average life is predictable within some reasonable spread, understanding what the life of the component is you're checking. What about the failures? One of the classes I do is in plants for operators and maintenance is equipment failure modes. Once an operator maintenance person understands how a piece of equipment can fail, they can make their PMs more effective. An example would be I do a webinar and I do training at plants called the 50 failure modes of electric motors. Understand there's 50 different ways an electric motor can fail. If you understand all those ways it can fail, it's a lot easier, a lot more beneficial to do the inspection. What if you have useful statistics? What if you're keeping track of mean time between failure? Those are useful statistics that help us develop time frequencies for PM. Goals of preventive maintenance. Another thing for your maintenance people, reduce equipment failures. If your PM's not doing that, it may not be effective. What about reducing the magnitude of equipment failure or the repair cost? What if we reduce the product loss or production downtime due to the equipment failure or repair? Reduce the deterioration in the productive capacity of the equipment. All things that are effective with a good PM program. And then the last one here, functions of preventive maintenance. Permit the asset to perform the function for which it was designed, purchased, and installed. Many times I go to plants, they don't even know what that is. I always ask the question, what was this machine designed to do? There was an example when a company was making wrapping crackers. The machine was designed to do 1,000 wraps per hour. They were trying to run it at 1,800. Well, the people didn't understand what that machine was designed to do. Ensure the safety of the personnel using the asset and the safety of the asset itself. Very important function. Ensure the asset continues to operate at specification and tolerance of design. What are those conditions? What are those specifications? Ensure the assets operates without failure or disruption, and maximize or extend the asset's useful life. All functions of preventive maintenance. What about subjective PMs? A lot of times at our plants we have these subjective PMs that say, check the pump or check the valve. So here's one I put in here just to jog your minds a little bit, but says on your plant rounds, make sure to inspect the block valve in the east pipe rack for any issues. So what are your comments on this PM? Inspect the block valve. Is this not a block valve? As we look at that, it's a block. It's a cinder block. Is it a block valve? Well, what is the definition? What are we inspecting here? Kind of a joke slide, but again, it stresses the point of what is our PM trying to find. It says make sure your PM test has common sense. What specific failure modes are you looking for? You know, what if your PM says check the belts? What does that mean? It might mean something to somebody that's been in maintenance or been around the plant for 20 years. What does it mean to a brand new maintenance person that's out there when he has a PM that says check the belt? Well, is he just looking to see if it's inside the guard? What is he actually looking for? So these are called subjective PMs. So the RCM process looks at components and equipment, determines how the components can fail. In RCM, these particular failure modes these particular failures are called failure modes. So every failure has the potential for a PM task. But again, we have to look at why we do the task, what's the cost of loss, what's the downtime. Maybe if there's none of those things, we wouldn't do the PM task. So again, to perform an RCM analysis, and I'm actually going to do one tomorrow for a company, but you pick a process in your evaluation or a piece of equipment. You list all the components in the process, and then for each of those components, you ask the question, how can or how has that component failed in the past? And then we're going to ask, how can we predict the failure with a predictive technology? We're going to ask the question, how can we prevent the failure with a preventive maintenance task, a PM? Or in some cases, how can we eliminate the failure? Can we redesign this component, make it more robust, do something to it so we can eliminate the failure from ever happening? Or the last question is, maybe if it doesn't have a payback for a predictive, it doesn't have a payback in a PM, there's no way to redesign it, what if we just let it run to failure? What if we just let it fail? Now, some of these are maybe low criticality, no safety risk or things like that, so we let them run to failure. But if you have that consequence, we need to have spare parts. We need to know where the spare parts are. But some of these items in your plant, maybe these are inspections that operators do. They don't cause a failure that's going to have any effect. Here's my RCM database. I'm actually going to use this tomorrow, where we actually list the failure modes. We actually have a functional failure here that says unable to operate at all. We have a failure mode that says the pump bearing fails to contaminated lube. We have an effect statement. We have an evidence statement. And we have an action that the operator is supposed to take when this failure occurs. Then there's a failure symptom. There's a low pressure alarm. That becomes a troubleshooting guide for the operator. Every time that alarm happens, we need to put in this database what he's supposed to do. So here he's going to try to restart the pump. He gets the low pressure alarm. He's going to call maintenance to troubleshoot repair. But there may be other things you want him to do. It's endless to what the information you can put in here. It gives the frequency, gives the downtime. You can put a probability consequence statement and make a priority on it. The priority can be anything you want it to be. It can be a 1 through 5 value. It can be low, medium, high. Anything you have high in here, you need to do something about. You can see on the right-hand side of my RCM database, it's evident to the operator, creates a quality issue, but here's other things it could do. Does it create an energy loss? Does it affect operations of rate? Does it affect downtime? Every time you select one of these boxes, it creates a report. We see some tasks to mitigate the failure. Develop procedures to filter lubricant and verify correct lube application. We're going to develop a PM around this. So as we put information in this database, it comes down to this report section here where you can select any one of these 16 different reports to find out if do you have any failures. Once you get the whole RCM done, I've got the quality box. So now we're going to look at all failures in this RCM analysis that affect quality of our products. So we select the quality box. And what it gives us all the failures that have to do with quality. If I select all the PMs that I've put in here, if I select the PM box, I can select all failures where we've said we need to develop a PM or a PDM. So the database develops all your reports as you're doing the RCM. It's a very effective RCM process, or a very effective RCM database. Very cheap. The cheapest RCM database on the market in the industry is about $18,000 to $20,000. It has licensing agreements and all kinds of gibberish you don't need. This database here is $5,500, and there's no license agreement. You use it on whatever you want in your company. And we do webinars to show you how to use this. We'll look at this later on in the year. But again, you have to have something like this sometimes to develop your effective PMs. This is what the airline industry uses to develop all the PMs around every airliner that's built. Now we know how effective the airline industry is. The nuclear industry uses it. We know how effective maintenance is in the nuclear industry. They don't have failures. So again, a process you need to consider. So this process using my software will develop the correct PMs and will be the start of your complete maintenance strategy. So again, one of the methods to help develop PMs. Now, one of the other methods we'll look at, this is called PM optimization. So RCM, Reliability Center Maintenance, looks at how components fail and what preventive maintenance strategies are effective. Well, the reverse of RCM, I always call this the reverse of RCM because now you have your PMs, so we should optimize our PMs. So PM optimization is a study of each PM task to prove it adds value and life to your component life cycle. So what I've given you here is a series of questions I would ask on a PM optimization. You know, a lot of this came from a class I went to with Ron Moore. How do you know the PMs you're doing are effective? It says here your company may be no different than most companies. You hope your PMs are effective. You hope you get enough time to do them this month, and you can count on the fact that people know what check the pump means. So how many PMs do you have in your system that are subjective like that say check the pump, check the belts, check the conveyor? Those are called subjective PMs. Again, we got to get away from these. So here's a statement here. Preventive maintenance is effective at reducing failures on only a few manufacturing equipment component failures. In order for a PM to be effective, it must be applied to the correct component at the correct interval, and the inspection must not be subjective. So we're going to talk about that again a couple of times. I'm going to make that comment. You cannot have subjective PMs and expect them to be effective. So here are two components at different facilities I was at. The one on the left-hand picture here, this motor that's all completely covered with dust and dirt, and a PM checked off the day before that the PM was completed on this motor. Now, when I saw this at the plant, we're trying to do PM optimization. I took a maintenance person that did the PM, and I took an operator from the area down there. And I said, so the PM was completed on this motor. Yeah, it was completed. So what I did, I took a temperature on the front bearing of this motor, and then I had the operator and maintenance person actually clean everything off the fan guard. We scraped all the dirt, crud, and dirt off the motor. We cleaned it up really good. And then I retook the temperature on the front bearing. The front bearing temp on this motor went down 35 degrees F. So again, once the operators and maintenance knew what the effects was of that, is motor temperature. Now, what does motor temperature mean to an electric motor? Well, for every 18-degree rise, every 18-degree Fahrenheit rise, or about 10 degrees C, you cut the insulation life of the electric motor in half. So here, by lowering the front bearing temp, lowering that motor temp 35 degrees, we actually extended the insulation life by almost 4 times. But once people understand this, once operators and maintenance understand this, there's more of a reason to clean that motor. So this became a every week PM for the operator. The operator had to take something and clean all that off and keep that motor clean. Makes the motor insulation windings last longer and more than likely bearing life. The picture on the right, a bucket elevator. And this was at a plant up in Canada. That's the St. Lawrence Seaway in the background. I asked the maintenance people, did you get all your PMs done on all the equipment? This happened to be a meal loading drag or a meal loading bucket elevator. It was about 120, 130 feet up in the air. So you had to climb a ladder to get here. So they told me they completed all the PMs. I go up there on Saturday morning to take a picture of the St. Lawrence Seaway, nice sunny day. This is what I find. Now, you think the person did the PM on this bearing the day before. I took my finger, dug down, found the greaser, through that crusty meal. The PM wasn't completed. So I asked them on Monday morning, why'd you check off the box that you completed it and it wasn't completed? Well, the wind was blowing real hard that day and the bucket elevator was shaking around. I didn't want to go up there. Well, that's okay. Good excuse. But don't check the PM off that it was done. Because if I'd have known that, I'd have carried the grease gun up there Saturday morning and greased the bearing. But what we ended up doing here, because of high winds, cold weather in this area, it gets to minus 20 in the winter, I put an automatic luber on here, a battery-powered automatic luber to make sure this PM task was always completed, so this bearing doesn't fail. PM, Here was a motor that failed on a shop floor in a company I was at. So I asked the maintenance, it's sitting on a pallet, failed motor. I said, why did the motor fail? Oh, it locked up. Bearings went out. Well, that's probably a generality of why it failed. But what do you think happened here with temperature? The same thing I looked at on another picture here. This motor should have been clean. There was no way it was cooling. Yeah, the bearings are going to fail. Probably the windings would have failed if the bearings wouldn't. I don't know really what failed until they took it apart. But again, that's just a general comment. It locked up. That's not why the motor failed. Some component in that electric motor failed. And I can tell you a couple reasons why it would have. So we can't have these kind of things in our plants. What's the PM task? Were we checking this motor every week or every month? What was the frequency? What was we looking for? Was it looking for hot bearings? But again, the PM task here, clean the motor. This was at a cement plant. Everything completely covered. PM task was done the day before. I'm not sure what they checked on it. The PM task said, check the gearbox on this piece of equipment. Well, how would you put oil in that? What is the failure modes around the electric motor we talked about when it's covered with cement dust? How would you effectively add oil to that gearbox or check oil in that gearbox without getting anything in it? It looks like the maintenance person probably wiped the coupling guard off to see if the coupling was actually turning. But again, what is the PM? Why are we doing it? Why is that grease gun laying underneath there? Hopefully they didn't grease the bearings with that grease gun, but how many different failure modes can you see in this picture that we can take care of? Now, once we do training with the operators and maintenance people here about equipment failure modes, the 50 failure modes of electric motors, you know, the 15 or 20 failure modes of gearboxes, the 30 failure modes of bearings, well, it becomes very obvious that there's many failure modes here. I would put a cover over this, a shroud of some kind to keep the dust off, to extend the life of these components. But again, what are we looking for? So an electric motor, again, we have to keep the electric motors clean. There has to be airflow across the electric motor. You know, one of the main PMs is to keep the back of this motor fan guard clean, keep the motor clean so we have airflow. Again, every 18-degree rise, you cut the insulation life in half. So our PMs have to be non-subjective. They have to say, what are we doing? What kind of failure mode are we trying to find? So the three previous slides, were there PMs or could we have performed, could there PMs we could have performed to reduce the chance of failure? And again, I ask this question all the time with maintenance people, is cleaning a PM task? Oh, no, we don't clean, we're maintenance. Well, somebody has to do the cleaning. What is the reporting method? What did you see? What did you find? Sometimes we can't find things, our maintenance people can't find things, our operators can't find things because we don't know what failure mode we're looking for. You know, one of my major customers, every 3 months, they went down for a couple of weeks. I went in there and trained all their operators about all the equipment components in their process, all the failure modes, so they knew what they were looking for. And then we walked out on the plant floor with cameras and notebooks, and we found failures. Well, now that plant is a lot more effective because now operators understand what they're looking for, and they turn in good information to maintenance. Now, operators in this case were union. They weren't allowed to do PMs, so we called it operator care task. These inspections were operator care tasks. We were finding failures because they understood how the equipment components can fail. Very good process. So here's my PM optimization form. Now, I can send you this if you want this. Just let me or Justin know. I'll send this to you in a Word document. I'm trying to get my programmer to make a database up, something like my RCM database for doing PM optimization. But this is what I usually do is I have this Word document and I make a list of the PM tasks I'm currently doing. And what are the frequencies of those tasks? And I start asking questions. Is the task necessary? Does the task help identify onset to failure? Is it an inspection? Is it an adjustment or calibration? Does the task help avoid failure, extend life? Is it a lubrication task, a measurement, a filter change out? Here's a question here. Is it related to a known consistent failure mode? Belt life would be an example. Grinder hammers. Flexible couplings have a known life based on temperature and operating conditions. Alignment's a key one there. DC motor brushes. Those all have known failure lives. We can change them out before they fail. The last question, does the PM task help me find or avoid a significant failure? You know, if you answer no to those questions, it says here, can the PM task be eliminated? Number 5, does the task have adequate specifications? So if we have a failure, we can take corrective action. So if you're checking V-belts, Does it just say check the belts? My maintenance crew brought this up to me years ago. Well, what do you want us to check? It says check the belts. So I went over this thing about, checking the belts for good condition, no slipping, flipping. If you can isolate it, do we use the tension gauge? What is that specification? Well, my maintenance guy says, yeah, but we're checking them when they're running. We need a tool. So we bought a battery-powered strobe light. Now we can take the strobe light, we can look in the guard, we can see the condition, we can actually stop the belt, see the condition of the belt. Is it shiny? Does it have cracks? We can look down on the shiv. Is the bottom of the shiv shiny? That tells us the shiv's worn out. So now with a tool, a little $300 battery-powered strobe light, we can actually do belt condition and shiv condition while it's running. So again, what are we looking for? Now, is the process for the current PM task, or what is the process for the current PM task? What's the frequency? Do we base that frequency of every week or every month on a known component failure rate? Do we have history in our CMMS files? Statistical analysis lets us mean time between failure, or Weibull analysis? Is it just best judgment, tribal knowledge? Have we just been doing it that way for years? Is there some regulatory requirement that sets the frequency? So it says for each PM task, high consequence of failure may increase the frequency of a PM or PDM task. Maybe if it's very low consequence or no consequence, we stop doing it. It says based on the above information, should the frequency be increased or decreased for the current task? Here's one that I used to tell my maintenance about. What has the task found in the past month or year to indicate the task is obtaining results? So I remember back in the early days when I became a maintenance supervisor, one of my maintenance guys would come in and he would have a stack full of PMs, and I'd ask the question, what did you find? There'd be a stack of 20 to 50 PMs. Oh, I didn't find nothing, everything's okay. My response to that was, wrong answer. If we're doing PMs, we have to have finds. You can't go through a whole department, a whole area of the plant with a stack of PMs and not find anything. So that's when I started doing my training. What are we really looking for? What kind of things should we find? I was always asking for finds. It said, what failure mode has been found or eliminated by using the task? Which got back into my training. What are we looking for, guys? Why are we doing the task? How can we eliminate that failure mode? Here, number 9, is the PM intrusive? Can it result in infant mortality issues? And I'll give you an example that happened at my facility. A maintenance person changed oil in a centrifuge and used the wrong kind of oil. Well, within 24 hours, the gears in the centrifuge failed. So here the PM task was kind of intrusive, right? We used to rebuild those gearboxes, and about 3 or 4 times over 15 years, we cut an O-ring putting it together, or we didn't get a gasket in right, and it failed a day or a week after we started. So a lot of times your PM tasks, you do these monthly and yearly things, can they result in infant mortality failures if we don't do the task correctly? It said, could any of the scheduled rebuild tasks be deferred or eliminated by using a PDM method? So here, as you start using these small handheld vibration tools, thermographic cameras, we go out and check a bearing with an ultrasonic tool. Do we want to come back the very next day and do an actual physical hands-on PM task? So a lot of times your PDM programs are going to eliminate some of your PMs. Number 11, very important. Could any of the items such as tightening, adjusting, lubricating, cleaning, or inspecting be done by an operator? It says operators can, in many cases, perform these tasks on higher frequencies and reduce failures. A lot of times people say, well, my operators can't do that. They're not smart enough to do that. We can't trust them. Again, those are issues you have to work around. The plan I was telling you about where we trained all the operators to do inspections, they become highly effective because they know what they're doing. They're trained. Is there cultures there like unions or a plant culture that's been in place for 30 to 40 years? Those are all things you have to work on to get your operators involved in doing some of these minor inspections. Now, they shouldn't be rebuilding gearboxes, but can they do a lube test? Can they at least touch the component? Can they listen, use their senses, and do these PMs? Can the PMs be consolidated by covering them all in one downtime or one service visit? A lot of times we can do that. Are there any failures or known failure modes that are not being covered during PMs? You'll find this out sometimes in an RCM or a PM optimization. Maybe we've missed a few PMs. Here's one here. Are there any hidden failures that need to be added to the PM program? Remember these failure finding tasks. I was at a plant one time where they hadn't checked the emergency stops in this department for 14 years. When they tested them, they'd been wired wrong since day one. But due to the fact I never have to use them, never tested them, if they ever were needed, they wouldn't have worked. Failure finding task. It says the optimization program we're looking at here should be reviewed every 3 to 5 years because PMs will change as the plant markets change, as the plant operating rates change. You know, there may be things you're checking yearly, but if you've doubled the rate or capacity of the machine, maybe they need to be done twice a year or every quarter, every month. The last one here, don't assume your OEM, your vendor PMs are correct, and don't assume everything you're doing now is correct. Review your PMs, a good process here to look at. Using all your senses. You know, what are your people looking for? When they go to do a PM, what is different? Using the sense of hearing, does it sound different? Does anything look different? Is there movement? Does it smell different? You know, sometimes when things get hot or oil starts getting oxidized, it'll smell different. You know, what feels different? Using that sense of touch, vibration, is there movement? You know, a lot of times I go around plants, sometimes I don't have a vibration tool, but I'll take my fingernail and stick it on the side of an electric motor, on the top of an electric motor, on the axial part of an electric motor bearing. Is there vibration? You know, sometimes I can almost tell they're not doing their alignment step right because of the vibration. What is the economic useful life of your equipment? This is a mean time between failure curve where this plot may be plots of different failures. So it's hard to do. I don't know if you can see the arrow on the screen, but let's say on this curve we have 1 failure in 6 months. As we go up the curve, we have 2 failures in 6 months. We get to the top of the curve, I have data that says we've had 3 failures. Maybe this is a V-belt. But if I know we had failures at 6, 7, and 8 months, my economic useful life of that component may be changed out the dotted line at 5 months. So if we have good data, sometimes we can change components out before they fail. Again, do we have this data in our system? Now, as a good reliability engineer, let's say I have the data, we start changing this V-belt out every 5 months because we know its life. The questions we need to ask may be, why is it failing in 5 months? Are we using the wrong method to change it out? Do we have the tension correct? Do we have the alignment correct? Is it the right V-belt for the application? Is it in an area where the temperature is too high? You know, the failure rate of V-belts, for every 18-degree rise, you cut the life of the V-belt in half. Is that V-belt in an enclosed guard where it runs hot? Lots of questions we can ask because we always want to extend that economic useful life. Here's a work distribution model. We use this similar to the one here at the company I came from. 15% of your labor hours dedicated to doing PMs. 15% of your labor hours dedicated to fixing items found from PM inspections. This means we need to find something with our PMs and we need to track that data. PDMs, predictive maintenance. 15% of your labor hours performing PDM inspections. 25% of your labor hours correcting issues found from PDM inspections, which just means we should find more things with PDMs than we do with PMs and put those in the work plans and correct them, tracking that information. 20% of your labor hours doing proactive tasks from that proactive side of the curve. You know, precision alignment, precision balance, precision lubrication, root cause analysis. And then 10% of your labor hours doing reactive maintenance. And we've talked about reactive maintenance, what that is, those things you do that aren't planned. Maybe it's things that aren't planned for 3 days. Maybe it's things that aren't planned for 24 hours. We have to track what our reactive maintenance is. We should be able to get it down. You know, I always say less than 20% is world class. The company I came from, they said they wanted to get it down to 10%. Again, how are you going to do that? Here's perceived world class. Less than 18% reactive maintenance, 47% of your labor hours doing preventive maintenance, and 35% doing predictive. Again, a different statistic than I just showed you, but again, this is what you're trying to do to prevent or predict so you don't have reactive maintenance. So asset criticality. How do we determine what PMs we're doing on what equipment? Well, remember, we're going to talk about this more in detail either next month or the month after, but what process have you used in your facility to determine what is critical? Sometimes I just came from plant, they just did an asset criticality, but they only looked at failures that cause production to be down. What about failures that create a safety incident, a fire, an explosion, somebody getting hurt? What about failures that create an environmental incident? Released atmosphere, a spill. If you're in a food plant, what are all the failures of the equipment components that cause a food safety incident or a quality incident? What about failures that cause operations to be down for an extended period of time? What about failures that are created by maintenance in their process of fixing it can cause more failures? But again, we rate all these processes from highest to lowest, all of our equipment, and it tells us where we should be applying our resources. Now, this is a cheap database we sell for like $400, but it goes to these areas at the top. You can see the safety impact, the environmental impact, the food safety impact, quality and operations. It gives you a rating in each area. Here's 160 in the quality area, but overall for all the areas, it's 450. So if you do all the equipment in your plant, and we come back and say anything above 700 is going to be A critical, anything below 300 is C critical, well, now we can develop PM strategies because we're going to say we're never going to miss a PM on our A critical equipment. Things stop failing. So this is one we use from the plant I come from. Everything that came out on that rating score above 700 was A critical. We never missed PMs on A critical equipment. Everything between 300 and 700 was B critical. We would miss those once in a while. Anything less than 300 was called C critical. We never did PMs on those. We'd have the operators check them. It took quite a few PMs out of our system. We were doing PMs on things that were not critical in any way. So this is the plan we used right here. It became very effective. We had less failures. We never missed PMs on critical equipment. So again, how are you going to use your asset criticality? Was the asset criticality done effectively in the beginning? So where are you on that PF curve? How much reactive maintenance are you doing? How much predictive maintenance are you doing? How much proactive maintenance are you doing? And what % of your time is preventive? You can't have 100% preventive and expect to be high on the curve. So again, we look at our curve again here. Moving from this left side, or the right side, excuse me, where you're doing a lot of reactive. Moving into how are we going to do more predictive? How are we going to predict these failures ahead of time? In the proactive here, what kind of things are we going to do in the proactive area? Because this is where we need to spend our time. But we need to change. We need to understand that our PMs are going to change as you become more reliable and become more effective. Where are you on this curve? Now we talk about precision work. And I use this slide. I always ask the question, is this precision work? And people laugh about this, but it is actually precision work. And the reason I call it precision work, because I don't know the factors around how this person was trained. I don't know what his written procedures are. But I always say to people, how many things are your maintenance people or maybe your operators doing where they take a little shortcut like this when they're supposed to be doing something precision because of what reason? Maybe it's time. If we're doing too much reactive work and we don't have a lot of time, maybe our precision work takes this shortcut. If we don't have a written procedure in place, do we take this shortcut? And again, when I talk about precision maintenance, do we need written precision documents for every piece of equipment in our plant on the rebuild? No, but once you do the asset criticality, once you determine what assets are critical, we need to do precision work. Precision work here. This company here, I won't say the name of the company, but this is a 150 horsepower electric motor they changed out. They were using one of the best laser alignment tools that you can buy, but a lot of bad practices here in doing this task. You can see the bolt on the right-hand side doesn't even come through the nut. The washer on the left-hand side, the washer's crushed down in the hole. There's marks on the side of the motor here where they beat the motor into position instead of having adjusting bolts. The base is not thick enough for the motor. It should be within 75% thickness. I've been in companies where it has to be 100% thickness of the foot of the motor. It's only half as thick as it should be, so it's going to create vibration issues. But here again, they had alignment in 1.5 thousandths in all three planes. Took them 7 hours to get there. They had smiley faces in all three planes. I don't know what the smiley face represented as far as accuracy. They didn't use torque wrenches on the nuts. But again, not precision work, but they obtained some precision results. But when I look at this picture, how long will this motor have stayed in alignment? Probably till they started it, because there's too many bad practices here that are not precise. Here's a precision balance technique on a PM. Somebody replaces an element on a coupling. The keyway should be 180 degrees from each other. And this slide here shows you that the keyway needs to be cut a specific length so that you only replace the metal you've taken out in cutting the keyway. Again, this is a precision task. But again, even if they're not cut the right length, put those keyways 180 degrees from each other. Creates closer to precision balance. But again, part of a PM task, precision work. Temperature and electronics. What can we do with electronics on PMs? Well, temperature has a huge effect. But here, they show most electronics, 55% is due to temperature, 19% due to vibration, vibration is 20%, humidity is 19%, dust is 6%. What are the failure modes? What kind of things can we look for in doing a PM task on electronics? So this gives you some idea. But again, we're understanding the failure modes, so know what we should be checking. So again, develop an effective PM, use RCM, use failure modes effect analysis, PM optimization to develop effective PMs. Use asset criticality to determine what equipment is critical. And again, we're going to do training on asset criticality in a couple months here. Never miss PMs on high critical equipment. Develop effective PMs that are non-subjective. Remember those subjective PMs. Check the pump. Always measure the percent PMs completed. I go through food and pharmaceutical plants where they say, well, I complete 99% of my PMs. Well, in studies I've done, they complete about 50% of their PMs. But they do 99 because that's what the audits recommend or require. PMs should be related to specific failure modes. So one of the key steps in developing a PM program is to understand how the component can actually fail. List all the potential failure modes of the component in your operating equipment. Again, one of the future webinars we're going to do this year is how to do an RCM analysis, how to cost effectively do that analysis to develop your maintenance strategy. Customer success story. This plant here, we did asset criticality, but you can see in the time study here, only 29% of their PMs were being completed. 56% of the work was reactive by definition. We did PM optimization. Now look, we did asset criticality and PM optimization. We got 53% of the PMs done, which were all on the A critical equipment and most of the Bs. Look what reactive maintenance goes to, 33% from 56. So we reduce reactive maintenance by effectively doing PMs. Huge success story. So again, the behavioral cycle of despair. This comes from Drew Troyer. Up here at the top, the machine breaks. We repair the machine. Why did it break? Poor design, poor installation, poor operation, poor maintenance. We do the blame game. Well, it broke because the operators didn't operate it right. Operations says it broke because maintenance didn't maintain it correctly. But if we don't do a root cause analysis, we don't know what really caused it. So we go down here and fix it. Sometimes we reward the efforts by maintenance by giving them a pat on the back. But it says here management's got to intervene. We can't reinforce that behavior. But what do? We operate the same way. We maintain it the same way. It's the same design, and we let corporate procurement repurchase the same cheap component, the same problem sometimes. Break the cycle of despair. Why do we need to do this? Because we have to compete. You don't want your 20, 30, 40-year-old facility not competing, because what's going to happen? You're going to get beat by the Lamborghini, and you're going to be out of business. All right, so the last question here, and you can answer this yourself. We're not going to go online and answer it. Do you think your PMs need some evaluation after this webinar? Again, answer that question. If you need help with this, get in touch with me or Justin. We can review this webinar. We can come to your facility, but I would say most of you are going to say we need some evaluation. Again, if you have questions, I'm not available today to answer the questions. This is a recorded webinar because of my schedule, but again, email the questions. I'll answer every question you email, and Justin will give you support from any way we can. Remember, if you need a download of, or if you need the recorded version, Justin will have that available. The PDF will be available, but improve those PMs. Thank you, everyone, for being on the webinar today. I'm hoping you got a lot out of it. Again, be ready for next month's webinar. It'll be another good one. Thank you.